Hello, hi, Assalamualaikum. My name is Muhammad Aswar bin Muhammad Basir. My registration number B1324102225, followed by our group members, Wan Akmal Mukri and Ikram. We are from Group 8. For a group project of force and factor safety analysis of an aluminium translatant. So the project applies equilibrium, stress analysis, and the factor of safety principle to evaluate the structural performance of an aluminium translatant. So our objective to develop an idealized model, draw the free body diagram, formulate the equation of equilibrium, analyze the external and internal force, and determine the maximum allowable force and factor of safety. The material we use is aluminium 6061 T6. Why we choose aluminium 6061 T6? Because it got the yield strength of 276 megapascal, with lightweight and strong. It also corrosion resistant and suitable for structural application.
Moving on to chapter 2, we conducted a literature review to establish the theoretical foundation to our analysis. So our research focused on 4 key areas. Truss structure, we rely on the principle that truss member carry only axial tension or compression, so with no bending moments, as noted by Hibler 2020. So this make them highly efficient for load distribution while minimizing material uses. So aluminium structure members, we choose aluminium 6061 T6 for this lantern. So aluminium alloy are ideal for temporary structure such as exhibition booth and portable podiums. So because they are provided reduced weight, so quick assembly and reliable structure performance. Structural stability and buckling. So using Euler theory, we recognize that long slender columns may fail at loads below yield strength. So therefore, we incorporated diagonal bracing into our design, which reduce the effective length of compression members and significantly improve buckling resistance. For factor of safety (FOS), finally, we define the force as the ratio of yield strength to working stress. So for public use structure, FOS of 2 or 4 is recommended to account for material variability, so unforeseen loads and manufacturing tolerance. So in chapter 3, so we define the methodology used to model our structure. So to begin with, identify our key structure component. So the top acrylic surface provided the workspace for laptop and materials. So the vertical aluminium tube act as the primary load bearing component, so under compression. So the diagonals bracing members are crucial for hence overall structure stability. So the base support plates convey the loads to the ground and prevent the unit from tipping. Regarding our analysis assumptions, we idealize the model by utilizing pin connected joint, which means we only consider axial force. We also assume static loading only, so with an applied load of 200 newtons center on the structure. So while neglecting the self weight of the material, the structure is built using aluminium 6061 T6 with a total height of 1.0 meter and outer diameter of 50 millimeter and the wall thickness of 3 millimeter. Next, we look at the physics of our design using free body diagram. So we apply a downward load of 200 Newton to the top. So because the lantern is a symmetrical, the load is split perfectly is in half meaning each support is 100 Newton. So by isolating the vertical tube, so we can see they're under a compressive load of 100 Newton. So we also use individual joint analysis to assure the internal force balance. To make sure the design is solid, so we use the rule of static equilibrium by assuming the force in the vertical direction. So we confirm that our support reaction are exactly 100 Newton each. So for load distribution, this proves that our vertical aluminium tube are effectively carrying the 200 Newton loads. Each tube handle 100 Newton of compression. So our diagonal bracing in the two is there to provide extra support. So handling either tension or compression depending on any side-to-side force. Thank you.
Moving into chapter 4, let's look at the stress analysis of our truss lectern. To understand how the material responds to the load, we first calculate the cross-sectional area of the vertical aluminium tubes. Given an outer diameter of 50 mm and inner diameter of 40 mm, the area equation gives us a total cross-sectional area of 443.8 mm square. Using the formula stress equal force divided by area, where our internal compressive force is 100 newtons, we calculate a working stress of just 0.225 megapascal. When we compare this actual stress to the yield strength of aluminium, 6061 T6, which is 276 megapascal, it is clear that the actual stress is exceptional far below the yield limit. Next, we determine the maximum capacity and the safety margin of our design. By multiplying the yield strength with the cross-sectional area, we found that the maximum allowable force per vertical member is approximately 120.5 kilonewton. This shows our 200 newtons working load is minuscule compared to what the structure can theoretically handle. By taking the ratio of yield strength to working stress, we get a factor of safety of 1227, while public use structures typically target a recommended force between 2 and 4. Our calculated force vastly exceeds this baseline. This confirms that the lectern can safely handle typical operational load with an incredibly generous margin of safety. So let's discuss what these results mean, alongside potential design optimization. The height factor of safety of 1227 demonstrates superior structural performance and confirms that the truss configuration successfully limits buckling and safely distributes loads. However, this also notes that the structure is significantly over-designed. So to optimize weight and cost, future iteration could reduce the tube dimension while still maintaining a perfectly safe structure. To improve practically functionality, we propose a few key upgrades, widening the base to lower the center of gravity and prevent tipping utilizing finite element analysis, known as FEA, to generate precise stress distribution maps and accounting for dynamic loading conditions like shifting weight or sudden impact to better reflect real-world event environment. So to conclude our presentation, let's recap the core findings of our solid mechanic analysis. First, our idealized structural model successfully shows a perfectly symmetric load distribution of 100 Newton at each base support. Second, the result working stress of 0.225 megapascal is completely safe against the 276 megapascal yield strength of the aluminium 6061 T6. And finally, our finalized factor of safety of 1227 prove that this aluminium truss lectern is exceptional, stable, and structurally reliable for any public use event. So that concludes our presentation. Thank you very much for your time. Assalamualaikum.